You are the host now, sir.
Yeah, I've done it. So you can see my screen, right?
Yes.
Okay. So we're looking at the geodesic vector field on the tangent bundle, and we want to look at what its horizontal and vertical components are, right? So we want to calculate d pi theta of j theta, g theta, and k theta of g theta, right? So at a point theta, which is PV in the tangent bundle. So we let gamma be the unique geodesic such that gamma 0 is P and gamma prime 0 is V. So then by definition of the geodesic vector field, G theta is the element of T theta Tm given by ddt at t equal to 0 of the curve gamma t gamma prime t in the tangent bundle, right? So therefore, what is d pi theta of G theta? This will be just gamma prime 0, right? Yes?
Yes. Yes.
So this is nothing but V. And what will k theta of G theta be?
This
will,
is 0.
right, it will be by definition, it will be ddt of the vector field along gamma prime, right? At 0. Yes?
Yes.
So this is 0. So that means J theta, the first component will be V and the second component will be 0. Okay, so this geodesic vector field, in terms of these sort of coordinates on the tangent space t theta tm rather, it just becomes v comma 0. Okay, this is the geodesic vector field, v comma 0. So this you can see in the picture, right? I mean, sorry, right. So if this is your geodesic, and this is P, and this is, so P is gamma 0, and Q, this is gamma T. Then the change in the foot is just this gamma prime 0, which is V. And since this is a geodesic, this gamma W equal to gamma prime T, the change in the head is 0, right? Because this is a geodesic. So that means that gamma prime is parallel along gamma. So when I transport V parallelly along gamma, I'll just get W. So the change in the head is 0, right? So that means k theta of G theta is 0. Is this clear?
Yes.
Okay. So the geodesic vector field in these coordinates, it takes a very simple form. It's just V comma 0. Okay. It's just V comma 0. Okay. So now I want to talk about the symplectic structure of the tangent bundle. But before that, maybe I should talk a bit about differential forms on a manifold, right? So are all of you familiar with this? How much do you know is what I need to know. So I need to talk a bit about integration of differential forms also over singular chains in a manifold. So do you remember differential forms in Rn? Yes, everyone is familiar with differential forms in Rn?
Yes, sir.
Anyone not familiar with differential forms in Rn? Anyone? Okay. So let me just do a quick recap quickly. So what are differential forms on a manifold? So let me do a quick crash course on differential forms. On M. So definition. So P element of M. So then wedge K TP star M. This is defined to be, this is the kth exterior product of the cotangent space. So this is by definition the set of T which are multilinear maps from TPM cross TPM K times to R. So this is a K-fold product. Such that T is multilinear and alternating. Right, so just like in Rn, we're looking at alternating multilinear forms, right? Okay. Yes.
Yes, sir.
Right. So remember, if del del xi this is a basis of TPM. Then dxi is the dual basis of TP star M, right? Yes? Yes?
Yes, sir.
Yes, sir.
Okay. So we know that once we have a basis of a vector space V, and we look at, say, EI, and we look at the basis EI star, the dual basis EI star of V star, the dual, then using this we can find, by taking wedge products of these EI stars, we can get a basis for any of these wedge K TP star M, right? For this space of alternating K forms. So then what will the basis be? It will be dxi1 wedge, K-fold wedge products, dxi1 wedge dxik, 1 less than or equal to I1 less than Ik. So the I1 to Ik are in strictly increasing order between 1 to n, right? This is a basis of wedge K TP star M. Is this clear? Right? Yes?
Yes, sir.
Yes, sir.
Okay. All right. So now definition. A K form on M is an assignment to each point P and M, we assign omega P, which is a alternating K multilinear form on the tangent space. So it's an element of wedge K TP star M. Okay. So this is a K form. So so locally, omega I can write with respect to the basis dxi1 wedge dxik once I choose coordinates. So then the coefficients will become functions of the point in the chart, right? So this will become a sum over 1 less than or equal to I1 less than ik less than or equal to n a I1 ik into dxi1 wedge dxik, where a I1 to ik are functions on the chart U in M, right? Yes? I'm just writing it with respect to the basis at each point. Is this clear?
Yes, sir.
So the coefficients will become functions of the point. And so we say that omega is C infinity or smooth if all of these coefficient functions are smooth. Okay. All right. So we can talk of a form being smooth. Okay. And so then the smooth K forms form a vector space. So we denote that by omega Km. Okay. So the space of C infinity K forms on M is denoted by omega Km. Okay. Fine.
Yes, sir.
Okay. So now, like we did for forms in Rn, we have pullback of forms. So if F from M to N is a smooth map, and omega is a smooth form, a K form on N on the range, then you can define the pullback as a form on M, F star omega, as follows. So you have to define the value on K tangent vectors, V1, V2, up to Vk at a point P. So you look at df at P. So these map to k tangent vectors at f of P, dfp v1, dfp v2, up to dfp vk. So this is in N, this is in M, and then you apply omega at the point f of P, and you get a real number. Okay, right? So we define the pullback f star omega. So this will be a smooth K form on M. So this is defined by f star omega at P applied to V1 to Vk is omega at f of P applied to dfp v1, dfp vk. Okay. Here P belongs to M and V1 to Vk belong to TPM. Is this fine?
Yes, sir.
Okay. So now, suppose I have my manifold M and I have a K form, then I can integrate that over what are called singular K cubes. Okay. So definition, a singular K cube is a smooth map in M C from the unit cube in Rn, in Rk, sorry, 0, 1 to the K, mapping to M. Okay. All right.
Yes.
Yeah. And so first, if omega is a K form, on M, then we can pull back omega by this singular K cube C. So C star omega, this is a K form on Rk, right? So this is a K form on 0, 1 to the K, which is a subset of Rk. So we know that in K dimensions, the K forms are given by just a function times dx1 wedge dxk, right? So C star omega is equal to H dx1 wedge dxk for some function H from 0, 1 to the k to R. Okay, we define the integral of omega over the singular k cube c to be the integral over 0, 1 to the k of H with respect to Lebesgue measure dx1 dxk. Okay. All right. Yes.
Yes, sir. Yes, sir.
What is this function H? We can give an explicit formula for H. So note, what is H of x? H of x I can write as H of x into dx1 wedge dx k applied to the basis E1 to Ek, right? Okay, so this is nothing but C star omega at x applied to E1 to Ek, right? Yes? All right.
Yes, sir. Yes. Yes. All right.
Yeah. So what is C star omega at x applied to E1 to Ek? By the definition of pullback, this is omega at Cx applied to dCx E1 up to dCx Ek. Okay, so thus Hx is equal to this omega at Cx applied to dCx E1 to dCx Ek. Okay. Fine.
Yes, sir.
So now note that this integral we can extend to linear combinations of singular k cubes. So CKM equal to the space of singular k chains in M this is defined to be equal to the free vector space over R generated by all singular k cubes in M. Okay, so just like you do in homology, you take singular case simplices and formal linear combinations of them. So here we're taking formal linear combinations of singular k cubes in M. Okay. So this is the set summation I don't know. I goes from 1 to M, lambda I, Ci, formal sum So m is greater than or equal to, well, you can have the empty sum, that's just the zero vector. So lambda 1 to lambda n belong to R, C1 to Cn, singular k cubes in M. Okay.
Yes.
All right. So why do we want to do this? Because then we can define an operator called the boundary operator. So for C, a singular k cube, and 1 less than or equal to I less than or equal to k, and alpha belongs to 0, 1, the I alpha phase, sorry, the I alpha phase of C to be the singular k minus 1 cube C sub I alpha. So this will be a function of k minus 1 variables, x1 to x k minus 1. So what you do is you take C, and in the ith spot, you insert an alpha. So alpha is either 0 or 1. Okay. So you insert alpha in the ith spot, and then you insert the rest of the xi's. So xi to xk minus 1. Is this clear? So this is in the ith spot. All right.
Yes.
Okay. Here's so x1 to xk minus 1 belongs to 0, 1 to the k minus 1. So then we define the boundary of C to be the singular k minus 1 chain, which is the sum I goes from 1 to k, alpha goes from 0 to 1, minus 1 to the I plus alpha, C I alpha. So now this is a formal sum of singular k minus 1 cube. So this is no longer a singular k minus 1 cube. It's a singular k minus 1 chain. Okay, so this belongs to Ck minus 1. Okay. And so then these C's, these singular K cubes are the basis of the space of K chains. So therefore, this delta is defined on the basis. It extends uniquely to a linear map from CKM to CK minus M, right? So then delta extends uniquely to a linear map delta from CKM to CK minus 1. Okay, fine.
Yes.
All right. Also note, for omega a smooth K form and sigma K chain, integral omega over sigma is defined by linearity. Okay. Again, the integral of omega is defined over the K cubes, which are the basis of the space of K chains. And so therefore, this extends uniquely to an integral over a linear function on the space of K chains. Okay. So this defines L omega, which is an element of the dual of the K chains. L omega is just given by integration over omega, integration of omega over the K chain. Okay.
Okay.
So we have a linear map. Phi from omega Km to CKM dual. Okay, so the dual of these K chains are called cochains, right? So we have a map from K forms to cochains. This space is called the space of singular cochains. So the map is, oh, I should have written this below. Maybe I'll just write it on the side. So omega maps to L omega. Okay. Is this fine up to here?
Yes, sir.
Oh. So to finish, let me just say that
Sir,
this.
and we used to define a homology here, right? Something.
Yeah, we're not going to need homology for now.
Okay. Okay.
Yeah. The homology, you look at the K cycles, right? The usual thing. The chains whose boundary is 0. And then you look at the K boundaries. That means the images of the boundary map. Those K chains which are boundaries of K plus 1 chains. And then you show that delta squared is 0. So therefore, any boundary is a cycle. So then you look at cycles modulo boundaries, right? And that is the kth homology HKM, H
Yes.
lower k, with
Yes.
real coefficients, with real coefficients.
Yes.
So I just want to say that this linear map phi is injective. In other words, any k form is determined uniquely by its integrals over all k chains. So in fact, by its integrals over all k cubes, because the k cubes are the basis of the k chains, right? So you just need to look at integrals over k cubes. And so here, so let me not write this as a lemma. I'll just so let's just do this little calculation. So suppose I have P is a point in M. So well, let's say so. Okay. So yeah. Okay. So P is a point in M, and V1 to Vk are tangent vectors at P. Okay. And suppose we let C be a singular k cube. Such that C0 is P and dC, the derivative of C at 0 applied to EI is the vector VI. Okay, for all I between 1 and k. Okay. So the picture is that here we have P and here we have, let's say, 3 tangent vectors. Okay. So V1, so k tangent vectors, V2, Vk. And then I have my singular k cube, C, which maps these vectors E1, E2, Ek. This is the origin. This is, so this is in M and P is C0. And so the image of the cube will look something like this. Well, okay. So bad drawing. Okay, let me try again. Okay. So, yeah. So it will look tangent like this. Okay. And yeah. So, something like this, right?